Hello everyone, welcome to the online meetup of GDG Cloud Budapest community. I'm Kamila Kesner, co-organizer of the group with Zsigmond P. Tóth, and we are going to be the host of today's session. I'm here to tell you some information, and Zsigmond is going to help out with the Q&A sessions today. Hi Zsigmond.
Hi everybody.
Okay, as usual, this meetup is a place for open discussions and sharing our knowledge and experiences, so feel free to join the discourse by asking your questions at the end of the presentation. We regularly organize events like this, so if you want to keep up with the latest news and technologies around GCP, join the community to learn from fellow clouders and experts of the field. Also, please check out our YouTube channel where we collect these videos. It is called Clouders Club. Okay, and before we start, let me tell you a bit of one of the main partners of the meetup group. It's Deutsche Telekom IT Solutions, DTITS for short. DTITS is the largest ICT employer in Hungary and a member of the Deutsche Telekom group. It serves its international corporate customers in the areas of software development, system integration, and operation. DTITS actively supports the operation of this community. The company sometimes takes part in the organization of meetups, providing resources, and often contributes to the life of the community with expert speakers from its colleagues. Since DTITS Hungary is a workplace that supports career building, professional development, and knowledge sharing, we are happy to share its career page with you, where you can find the currently open positions of the company. Please scan the QR code if you're interested, and it will take you to the career page of Deutsche Telekom IT Solutions. And that's it from my side. Thank you for your attention. And with that, I would like to give the word to our speaker. Hello, Abdel, the stage is yours.
All right. Well, hi, everyone. Thank you for having me. My name is Abdel. I'm based out of Stockholm, Sweden. I'm actually a developer advocate at Google. I've been at Google for almost 10 years. My background is software engineering, but over the years, I have kind of done a little bit of everything. And now I mostly focus on Kubernetes and containers. It's my two main areas of focus, and generally speaking, cloud native technologies. And so today we're going to talk about this thing called software supply chain security. It also goes under software security, software supply chain security. It has multiple names. I'm going to attempt at explaining what it is and what problems it tries to solve, and why this is important, and why specifically, if you are a developer, you should care about these kind of things, right? So starting with breaking down what the term software supply chain security actually means, it's kind of like a very heavily marketing buzzy term, which literally means, or we can take the whole sentence and just break it into three parts: software, supply chain, and security. So the supply chain of software is essentially how do you get software from where you produce it to where you use it. So there is multiple things that can go into these two terms. CI/CD can be included there. All your DevOpsy, DevSecOpsy practices can be put in there. Where do you get your dependencies from can be put in there. But essentially, it's the overall methodology or set of methodologies, including software, tools, people that are involved in producing software, from code all the way until it's either a binary that we run in production or some sort of dependency. And the software supply chain security movement is trying to make sure that these huge mechanisms that we put behind shipping software is secure, or as secure as possible. So anybody who have done anything around software supply or software deployments before, or software development before, you know that your code usually starts at some sort of source code that you write, and then a bunch of dependencies that you pull from somewhere. Either you pull them from the internet if you are working on some hobbyist project, or if you work in a company that takes software supply chain security seriously, then you probably have your own internal tested and vetted and approved set of dependencies. You put these two things together in what typically we call a build system. You build your code, you package it, and then you ship it. So the shipment part could be either to the runtime or to a repository as dependency, right? But like the thing that probably not a lot of people realize is that even your dependencies are actually produced the same way. So it's sort of like a perpetual, never-ending loop around the same mechanisms that we use to ship software. It's just that your dependency is not a binary. It's typically some sort of a library, right? And so what have been happening over the last few years was a massive increase in the number of attacks that are leveraging software supply chain security and trying to hurt or to come at people. Generally speaking, as an IT field, we are doing better on securing endpoints, devices. I mean, it's not perfect, but it's still better than it used to be 20 years ago. But the interesting thing with software supply chain security and the dangerous part of it is that we sort of like just blindly trust open source without really verifying it. And we don't make sure that we are using things that are like vulnerability free. So there are a couple of examples here. You all heard of Log4j last year. There was SolarWinds, and there was a bunch of them. I will give you a more precise example. There was a big supermarket chain here in Sweden where I live that was attacked in 2022 with a software supply chain security types attack. And they had to shut down anywhere between 24 hours to 6 days. They had to shut down all their stores. They have about 700 stores across the country. And the reason, because that big supermarket chain was using a third-party vendor, and that third-party vendor managed the supermarket cashier system. So the devices that are used by the actual cashier that scan your articles to pay, or the self-service checkout devices, which are like the where you scan yourself the articles. So that vendor or that third party that the supermarket company outsourced the management of these computers to used an off-the-shelf software that they bought. And then at some point, there was a patch of that off-the-shelf software that was released or made available. And the vendor installed that patch into the supermarket computers. And then they ended up with a backdoor. And once it was detected, it was like a ransomware, and they had to shut down for like 4. So this illustration is really to demonstrate, to show that this problem could begin at a very small level and then could be amplified just because we are in a situation, generally speaking, whether you are using open source code or even closed source third-party software, we just depend on other people's software. And that's because the supply chain itself, which again, a fancy term to say CI/CD, can be attacked in so many ways. I mean, you can have people injecting bad code, either maliciously or not maliciously. So maliciously is the worst case scenario, which is people that you hired and you probably background checked, but they have been secretly trying to steal your IP, your intellectual property, or trying to hurt you or something like that. And maliciously, people make mistakes and people write bad code all the time. You can have a compromised source control system. You can have a compromised build system. There was also another example in 2022 of a very popular managed CI company that got all their AWS keys leaked. And then they were not aware for like about 2 weeks. And that was a massive problem for their customers. You can end up also with something with like a package that you download, which looks good. You maybe static scan it. It looks okay. You look at the code, doesn't look weird inside. And then once that package is inside your production system, then it will download like a worm or backdoor, like run a bash or a curl against like a remote thing, and then just download some sort of backdoor and install it. And then you end up with a vulnerable software. So what have been happening over the last few years is that security professionals have been borrowing certain like protections that already existed. The two main ones I want to talk about today are zero trust and shift left. So in the context of software supply chain security, zero trust essentially means establishing trust in the software itself through the entire chain, from development all the way until runtime. And I'm going to show you an example today of how that looks like. Shift left is essentially making sure that people who are writing code are aware of what they're doing. And I'm going to talk about a very specific example. We do have a couple of products on Google Cloud which we offer that can help with this shift left movement. Some of them are free, some of them are commercial. I'm just going to focus on the free ones because I'm not trying to sell you anything here. So one of these major efforts is a company, or rather a project called Sigstore. So Sigstore is a group of companies that got together and they are building software, so tools and also frameworks that are attempting to solve the software supply chain security problem for open source. So one of these frameworks is a framework called SLSA. It's written SLSA, but we read it SLSA, which stands for Security Levels of Software Artifacts. And what it is, it's essentially a checklist with a list of best practices that you should implement in your software supply chain security. And depending on which requirements do you meet, you can say that my supply chain is compatible or compliant with level 1, level 2, level 3, or level 4. I'm going to show you an example later of what those lists are. And then they also build a bunch of infrastructure and software. So we're going to look at an example today called Cosign, which is a command line tool that works with containers. If you use containers, it's pretty cool. And then they also have like a certificate authority. They have a way for people to get certificates, etc., etc. And so the way it looks like, or the way Sigstore thinks about software supply chain security is this way. As a developer, I write some code, and before I publish my code, I request some sort of certificate. So Sigstore have something called Filusio, which is a place where you can request a certificate to sign, or you can use your own public or private key infrastructure. So you would sign your artifact, and then you would publish the artifact, the signed artifact, but also publish the signing certificate itself. And in the signing certificate, you will have the public key. So that way people can actually take that artifact and use the public key to verify the signature. All of that gets published to something called Recore. So there is actually a public ledger. Recore is a public ledger, which is a transparency log ledger that contains basically traces of software being signed. You could, as an end user, either look into Recore to see if something have really been signed, or basically just download the certificates and verify the signature yourself. This is such a super long, super complex way of explaining essentially when you go and download a very basic like binary and you have a SHA-256 or an MD5 sum, and then you download that file and then you use the command line to verify if the signature haven't been changed, right? So for SLSA, I said there are 4 levels. This is how the SLSA framework looks like. So I'm not going to go into the details of what each level is, but I have to stop here to because a lot of times when I present those slides, people get overwhelmed because they think, oh, that's a very long list of things that people will have to do to meet SLSA requirement for some level 1, 2, 3, or 4. Generally speaking, security is not an end goal. It's not something that you as either a security professional, a developer, a CISO, a CTO, or whatever your role is. It's not a project that has a fixed term. It's not something that you should aim for and say, I'm going to run this project, and by the end of the year, I should have security done. Check, move on, happy life. That's not how it works. Security is a continuous improvement process. You have to continuously test and make sure your systems are as secure as they should be. And this framework presents a list of practices that can be implemented gradually, one by one, as you make progress, as people get also familiar with them, because one of the biggest challenges of security is that they introduce change, and people don't do very well with change. So you should look at it more as a continuous improvement framework rather than just something you have to implement for compliance reasons. SLSA is not really a government thing. This is not ISO or any sort of other, like a standard certification. This is just a set of best practices published by companies that have been doing security for a very long time. And they tell people this is what we think a software supply chain security should look like. I wanted to make sure that people understand this. And the last key in this puzzle is something called SBOM, or Software Bill of Material. You probably have heard of SBOM. It's going to be very important to understand what SBOM is, and even required for some companies. By 2025, the EU, the European Union, passed a law that forces some companies operating in certain sectors like finance, healthcare, etc., energy, to actually have SBOM for their software generated and available for when the regulators ask for it, sort of like GDPR, right? So what SBOM is, it's essentially metadata that you store with an artifact that tells you what's inside that specific artifact. So if you have a piece of software, the SBOM is the list of the dependencies that are used to build that piece of software. And there are many, many ways you can generate SBOM. You can generate into different formats, either CycloneDX or SPDX. And then depending on your build tool, if you're a Java developer, Maven, for example, have an SBOM plugin. If you are a Docker developer, Docker itself has an SBOM feature, like an experimental feature. I'm not sure if it's experimental anymore. But yes, there are tools that you can run against your software. It generates the SBOM, and then the SBOM is a file. And then inside that file, you have the list of the dependencies and what licenses they have been released under, where those dependencies came from, who is the author, when, etc., etc. You have all this information. So putting these two things together, SLSA, Sigstore, and SBOM, these are 3 different components that can be implemented independently from each other or together at the same time. Starting with, in my opinion, the easiest is always SBOM, because it's something that you already have the artifact. It's just another step to generate the SBOMs. SLSA is essentially a framework to give you a tamper-proof process for producing software. And then Sigstore is the company that makes both SLSA and it's not a company, it's a project that makes both the SLSA framework, it makes some tools for SBOM, and it makes some tools also for Zero Trust, which I'm going to show today, actually, right now. So I'm going to take a very simple example. This is a very stupid example. I hope that my command line is big enough for you to see. I have a very simple app here, a very basic container image, which I'm going to go ahead and build. Give me 1 second. Yes, there we go. So it's going to take a couple of seconds to build. We're just going to wait for it. So it's a very simple app, very simple Go app, which has like a Docker file. Nothing too fancy. Yeah, I use multi-stage build. So I have the Golang container to start with. And then I have a very minimum Debian container in which I basically copy the actual application and start it, right? So very simple application. So if you have never worked with Kubernetes, I'm going to do some stuff with Kubernetes today because it's just easier for me. But you can think about it as just a deployment target. It's just a place where I'm deploying the app. So if you don't really know Kubernetes that well, don't worry about it. So I'm just going to go ahead and tag my image. Docker tag is a command line to tag the image, for those of you who doesn't know. So I have 2 images. I just tagged them with 2 different names. I called one unsigned and one signed. Just stuff that would make sense in a second. Now I'm going to go ahead and take that unsigned image and just push it to a remote repository. So I'm using artifact registry in Google Cloud. It's our artifact registry, but this actually will work on any artifact registry, including Docker Hub itself, or any container registry, sorry, including Docker Hub itself. So I'm just going to wait for this to finish. I'm going to actually show you here really quick. I have my container image here. It's called the Hello World Unsigned, and it's been uploaded. It's one of the cool features we have on this particular thing called artifact registry is continuous vulnerability scanning. So it will continuously scan my images if they have vulnerabilities and report them. That's part of this thing I talked about called shift left. Basically, you give the developers the possibility to see what sorts of vulnerabilities their code might contain. But anyway, so I'm going to take that image and I'm going to do something very basic. I'm going to deploy it into Kubernetes, right? Again, don't understand Kubernetes, that's not a problem. Just don't worry about it. Just think about like if I took my container image and I just pushed it to a server, right, to deploy it. So normally, if I do this, this should just work because Kubernetes is designed such a way that it doesn't actually verify. It says that it already exists. So let me delete it and just to show you that it actually works. Delete, deploy. So Kubernetes is set up such a way that it doesn't really verify if something should be deployed or not, right? So literally, I could be deploying to my cluster whatever I want. And by whatever I want, it's my workload I just deployed. So this is just a random container I built. And what I'm trying to show people here, or what I'm trying to get you to understand is think about this as a random container you pulled from the internet and deployed. You had absolutely zero idea of how this thing looks like, what's inside of it. You just like deployed random stuff from the internet, which is not great. So what do we want to do? How do we avoid this? How do we establish trust? How do we make sure that the people that built the image and shipped it are the actual people who claim they are who they are? Well, there is one way we can do this. I'm going to push the image one more time again, and then I'm going to use cosign. So I'm going to copy this and I'm going to explain it in a second. So cosign, what it is, it's a command line tool that can use a key. So by key, I mean an asymmetric key, a private public key pair, to take a container image and sign it and push the signature as metadata to that container image, such a way that I have a piece of metadata that I can use to verify the origin of the image. So cosign, sign, I give it a key as an input, and then I give it my container image. This key is coming from Google Cloud. We have a service called KMS, Key Management System, but cosign itself is designed to be agnostic. It can basically literally work with any key management system, AWS, Azure, Amazon, whatever. So it's going to push the signature to my container image, and then I will show you how that looks like in a second here. If I go back, yeah, so my container image is here, it's pushed. And then if I go look inside, I will see that I have actually 2 pieces of artifacts inside that container image. And if I click on this one and look at the manifest, I can see that there is the signature. So that's the unique signature of this container image. If I change a single character inside my container image, the signature will be different. Now, what I did is I built a container, I pushed it, and then I established trust. I signed it with a key, and now I can just publish my public key, and anybody who has access to the public key and have access to the actual container itself can just take these two things together and use cosign to verify that the key was signed by me, right? So I run cosign verify with the same key and the same container image here. And it says the cosign claims were validated. The signature was verified against a specific public key. And this should give me an exit code of 0. So if I am doing this as a part of a pipeline, I can just run verify. And if the exit code is 0, I know that the verification passed. If it was non-zero, I know that the verification didn't pass and something failed, and I can fail my pipeline. Good. So now if we want to go a step further, again, Kubernetes has a mechanism called admission controller, which is just like a little code, like a piece of code that you deploy and you tell it to verify certain conditions or policies before allowing anything to happen in the cluster. I've already deployed my admission controller and I have already created a policy. And in this policy, I'm just saying for all the images, I want you to verify the signature against this key. It's the same exact key I used earlier. So now, if I go, you remember earlier when I was able to deploy stuff into Kubernetes without really verifying that they are signed or verifying where they are coming from? While using this policy controller, I can do this. So I'm going to create a test namespace just to illustrates the points. I'm creating a namespace called test, and then I'm putting a label on it. And this label is policy.sigstore.def include true. This particular policy controller I'm using requires the label to work. So you have to deploy it, and then you have to label a namespace. And that basically means that the policy controller will apply the policies to that specific namespace. Now, if I try to do the same exact thing I did earlier, which is I deployed the non-signed, non-verified, I don't know what the origin of workload, that should just fail, right? So if I take this command line and I pass it here, and I'm trying to create a deployment, and in that deployment, I am using the unsigned container image, and I'm trying to deploy it to the test namespace, this should fail. And it will fail because it will tell me, it will say blah, 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 somewhere. Signature key validation failed for authority for Europe, blah, 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 blah. No matching signature. So essentially, it could not verify the signature of that container image. However, if I try to deploy the one that have actually effectively been signed, that should just work. All right. Yeah, that's it. So that's just works. So nothing too crazy here. Yeah. So essentially what I did is I built a container image, I signed it, established trust, and then I had a way to verify that the container image have been signed before allowing it to be deployed. Very basic demo, very basic example, but like this illustrates the points of like verifying trust. So very quickly, I'm going to just run you through some free stuff we have on Google Cloud, and then I want to leave some time for questions. We have this thing called Software Delivery Shield, which is just a set of products. Some of them are commercial, some of them are paid. I'm going to skip the commercial ones. We have a plugin called Google Cloud Code. And this is a plugin that you can install in Visual Code and IntelliJ. And inside this plugin, we added continuous vulnerability scanning for dependencies. So for now, it works for Java, Node.js, Go, and Python. It will look at your dependency file, whether your pom.xml or your requirements.txt, and it will just scan those dependencies and run them against a CVE database, and then give you in the editor reports about which dependencies have which vulnerabilities. This is free. It's still in preview. We haven't made it to GA yet, but you can use it. It's free, right? So Google Cloud Code is the name of the plugin, and the name of the feature is Google Cloud Code Source Protect. We talked about artifact registry and container analysis. That's basically when I push the image, they get continuously checked. Those are paid feature. However, we have something called assured open source software. So what's assured open source software? They are essentially a bunch of very popular Java and Python packages. There are about 300 of them as of now, but we're adding more. And those are packages that we download, we fuzz test, we verify, and then we make them available to people for free. Again, you don't have to pay for those, they're free. So assured open source software. I'm going to skip this, and I'm going to skip that as well. Well, actually, no. If you are using Google Cloud, and specifically if you are a GKE or Cloud Run user, there are these two features, which I can really show you really briefly. I think they're cool. Even if you have to pay for them, I think it's still worth showing them because I think they're cool. If you go to GKE now, there is this thing here called security posture. And if you click on it, it will basically give you like a dashboard that shows you vulnerabilities that you might have in your running containers and also misconfigurations. So it's able to see things like privilege pods. So if you have a pod that has privilege or can escalate its privileges, it will tell you who these pods are, which container are there, and then also give you a way to fix them. So propose a way to fix them. And yeah, so like, for example, this is a pod that has a container that is allowed to run as root, etc., etc. It's like a bunch of things like that. That's it, I think. So to sum up this is what we think how supply chain security should look like. We have a bunch of tools that can be used independently, but the beauty of all of this is that the frameworks themselves and the best practices are actually open. So you don't really even have to be a Google customer. You can be a customer of any other company, or you can have your own self-hosted stuff. And the tools I showed work for open source software. So Cosign works for any Kubernetes installation, for any containers. They don't have to be our containers. So yeah, that's basically the TLDR. I hope this was useful. And if you have any questions, I am all ears.
Okay, so let's check the questions from the chat. So one question from an attendee is the following. What are the best security scanning tools for pipelines and preferably the open source ones?
I don't have any on the top of my head, to be honest with you. I can mention one. There is something called Project Graphias. I think it still exists. Yeah, Project Graphias, if people are interested in it. This is actually a set of open source tools that contain also things for scanning for software supply chain security. I would look at this. It's pretty interesting. But like there are tons of them. And unfortunately, I don't know anything from the top of my head for now. So sorry.
Okay, there's another question. It is related to Cosign, and despite if the key was verified, but the contents of the container has issues or malicious code, but it was not detected during development. So are there any best practices for such scenarios when it's not detected, but there is something which has issues?
Yeah, I mean, static code analysis would be one way to go, is you analyze the code before you build the container itself, right? So the cosign is only good at making sure that the container is signed by the people you trust. And what I mean by people, it doesn't necessarily always mean actual people. It could be like a CI system, right? It could be part of the build system executing cosign to sign the container itself. But essentially, that this thing is signed by something you know. What's inside the container, cosign is not aware of it. It doesn't see what's inside the container. So I don't think that there is really something specific that cosign can do in that sense. However, I think I know where the answer is coming from. If you end up having a problem with one of your containers and you detect later after you run it that it has a vulnerability, if you want to invalidate that container, you can just invalidate the key itself. So the key that have been used to sign the container, that key can be invalidated. And once you invalidate it, then the key is not valid anymore, then the signature or the verification will fail and the container will not be able to run again.
Okay, thank you. There is another question. These tools that we have just discussed, are these good against malicious, so detecting malicious code only, or for detecting bugs when something was not implemented the right way, although the intention was not something
Malicious.
negative, it was just by accident there was a bug?
Yeah. So that's a two-part question. Detecting bad code, I don't think that can be 100% achieved with tooling. You still need humans to be involved. So in my opinion, the best way to actually make sure that people don't make mistakes is to have peer reviews, right? Make sure that before it gets committed, that somebody else review it. That's what we do at Google. If people are curious, every single piece of code, every single pull request has to be peer reviewed by somebody else. You cannot just push code randomly, right? That's just starting there, right? And we even have like an internal champion program. It's called readability. So you as a person, after doing a bunch of reviews for a specific code, for a specific type of code, like the programming language, you become like expert by having the readability. So you become Python readability or Go readability. And that means basically you reviewed enough code that you know what the code size should look like. And you also know what the best practices around that code in programming language are specifically should look like, right? So this is like a practice I encourage, generally speaking. This is to start the thing. Then you have tools to do static code analysis. Those typically are okay at detecting like the very basic mistakes that people make when they're writing code. But beyond that, the vulnerability scanning would be also a very good way to detect problems post-build. So after you have built and push your code, you can just have continuous vulnerability scanning turned on to detect malicious attacks. There are, if you care or you are curious, there are actually tools that can monitor workloads at runtime and make sure that they don't do anything malicious. We have one called CTR, which stands for Container Threat risk or something. It's a Google product. It's open source, so you can just download it. So that can monitor containers when they are running in Kubernetes specifically. But I think that that's all I have for answering your question. So I think you have to clearly sort of like split the problems before building and after building. And those two problems have two different ways of solving them. So pretty much everything I covered today talks about the post-building, but pre-building, like code reviews and like having proper code style that you enforce internally. And also you check at the runtime to make sure that your code is linted properly, etc., etc. These are like common practices people do.
Okay, thank you. That answers the question. I don't see anything else in the chat from the audience. Should there be anything, then it's the right time to ask. Okay, thank you very much. So that's all regarding the questions. So back to you, Camilla and Abdel.
Yes, thank you very much. Let me thank you, Abdel, for your insightful presentation. We are very happy that you could join us today. And also would like to thank the participants for joining us. I hope you enjoyed today's session. Don't forget to join the GDG Cloud Budapest community so we can meet again. And thank you again. Have a nice afternoon. Bye-bye.
Thank you. Bye.
Thank you. Bye-bye.